When you're solving a system of three equations in three unknowns, if they're linear equations, then each one of these equations defines a plane in space. So this is the equation of a plane, that's the equation of a plane, and that's the equation of a plane. Now usually three planes, if they have different tilts, should intersect in a single point, but you got to be aware that that doesn't always happen. Here's kind of a picture of the simplest case. We have these planes, and definitely they're kind of in some sense all perpendicular to each other, and you can see there's just one intersection point there right in the middle. This would be like in a building where you have the floor and two walls. The floor and this wall intersect in a line, and this wall and this wall intersect in a line, and this wall and the floor intersect in a line. So there's three lines, and those three lines all come together in this single point. Now, even if the planes aren't perpendicular to each other, they don't have to be that. In general, they'll cross still in a single point. For example, if you look at the in this problem, if you look at the red and blue planes, they cross in a line, and this red plane with this greenish one, they cross in a line, and this blue plane with the greenish one also cross the line, and all three lines come together in that single point. So usually when three planes cross, you get a single point, but that's not always the case. Cooked up some examples here. Here we have three planes intersecting, but these two planes intersect in a line, and these two planes intersect in the same line, so the intersection, instead of being a single point, is a whole line of points. So now, instead of being locked down to a single point, there's some freedom. You can move back and forth along that line. So one variable is free, and then knowing that variable, you can determine the others to locate a point on that shape. So you could have sort of a one-dimensional line of solutions from finding where those three planes cross. Here's a case where you have no solution at all. I cooked it up so that the planes, maybe a little bit like a tent, like a pup tent that you could sleep in here. There's a line here where the floor and one wall of the tent, and then there's a line where the two walls of the tent come together, and a line where the tent hits the ground over here. But those three lines, I cooked them up so that they would be skews. They never cross, and so there's never a solution. There's not a point. There are plenty of points that lie on the two slanted planes, and plenty of points that lie on one side of the one wall of the tent and the floor, but there aren't any points that lie on all three. So you may not be able to solve a system of equations in three unknowns. Here's another one that has no solution. I just made them like the three planes are like the first floor, the second floor, and the third floor, and there are no points that are in common on those three planes. So, okay, you can also get situations where maybe all three planes are the same plane in disguise, and so there's actually a whole plane of solutions. That could happen. That would be a two-dimensional plane. So either there's a single solution, or there's no solution at all. There could be a single solution, which would be zero-dimensional. It's just you're locked into being at that one point. There could be a line of solutions. There would be a one-dimensional solution, one freedom. Or there could be a whole plane of solutions so that there were two freedoms. I just want to show you what it looks like if we use our rules from before. Remember, we said you could switch any two equations, and the solutions to those equations would stay the same. You could multiply any equation through by a non-zero constant. That, of course, means you could divide as well, and the solutions would stay the same. And you could add any non-zero multiple of one equation to another without changing the solution. So we've got those three steps. I apply them. I want you to see what happens in a system that's inconsistent, so that there's no solution, or a system that's dependent, so that there's a whole line or plane of solutions. Let's start with this one. Now, the way I've set this up, actually, I like to use the simplest one to eliminate the values of the x and the other. So I'm going to just switch equation 1 and equation 2. This is my notation that reminds me what I did. And the reason I'm switching is it just makes the arithmetic a little bit easier as I change this system slowly into echelon form, that staircase form. Now that I have them switched, it's easier for me to see how to use equation 1 to eliminate these x's, trying to get down to this echelon form. By the way, doing this is a procedure called Gaussian elimination. So taking a system and moving it towards an echelon form is part of what's called Gaussian elimination. So what we plan to do is Gaussian elimination to echelon form and then back substitution. Okay, I can see the best way to eliminate these x's is to take negative 2 times equation 1 and add it to equation 2 and use that to replace equation 2, and I could take negative 3 times equation 1 and add it to equation 3, and then the x's will cancel, and I could make that my new equation 3. So if I go ahead and do those steps, let's see what system we get. Notice I'm only changing equation 2 and equation 3, so I'm hanging on to equation 1, which is x plus y plus 2z equals 4. If I take negative 2 times equation 1 and add it to equation 2, of course the x's disappear. Negative 2 times y is negative 2y, plus negative 3y is negative 5y. Negative 2 times z is negative 4z, plus 5z makes positive z. And negative 2 times 4 is negative 8, plus 4 makes negative 4. Next plan is to take negative 3 times equation 1 and add it to equation 3 to get a new equation 3. So negative 3 times x plus 3x makes no x's. Negative 3 times y would make negative 3y, and negative 2y make negative 5y again. And negative 3 times 2z would be negative 6z plus z. And negative 3 times 4 is negative 12, plus 9 makes negative 3. Okay, now you might see a problem right here, because negative 5y plus z has to be negative 4, but negative 5y plus z would also have to be negative 3, and that's going to be impossible. Well, let's say we didn't notice that just yet. Let's just keep going. Well, if I want to, I've got the first part of my first big step in. I want to take this out so that I'll have this in that staircase or echelon form. So I can see I need to take negative 1 times equation 2 and add it to equation 3, and that'll eliminate these y's, and that'll give me my new equation 3. So notice I'm not messing with the first equation, so I'll just copy it down, and I'm not changing the second equation, so I'll just copy it down as well. And now I'll take negative 1 times equation 2 and add it to equation 3. So, or you could think that's the same thing as subtracting equation 2 from equation 3, since subtracting is adding the opposite. Negative 5y minus 5y, of course the y's disappear. We planned it that way. But now we get z minus z, that's 0. So there's nothing over on this left-hand side because the y's and the z's canceled. Over here, negative 3 times negative 3 minus 4 is the same thing as negative 3 plus 4, which is 1. Okay. Well, this tells me that I added one equation to another equation, or actually subtracted one equation from another equation, which means as long as the second equation is true, then the third equation can't be true because it gives me something that's never true, right? So 0 equals 1 is never true. Now I know I'm in trouble. There's no choice of x, y, and z that would make this true, and so there's no solution. We'd say the system is inconsistent.